So suppose that we have a nice Heegaard diagram. So as every Heegaard diagram, it determines a three-manifold, closed-oriented, compact three-manifold Y3. And let me just remind you what nice means. So nice means that if you take this decomposition of the complement of the curves into components, the components I will call elementary domains. Then DI is either a bigon, so it looks like this, or a rectangle, so it looks like that. You see, and there is nothing in here. Or there is a WI which is in DI. So either a rectangle or a bigon, or it contains a base point. And recall also that each component of the complement of the alpha curves contains a unique base point element of W, and the same for the sigma, the complement of the beta curves. So that's sort of built in the definition of a Heegaard diagram, a multipointed Heegaard diagram. Okay, so we have a nice multipointed Heegaard diagram, and we will associate to it a chain complex. So the chain complex CF hat, so this depends on the actual diagram, is generated, so is a Z2 vector space. So it will be a finite dimensional vector space over the field Z2, because I don't want to deal with signs, but in fact the whole theory can be extended to like finitely generated abelian groups, so we can do it over Z. But let's stick to the Z2 choice, generated by so yeah, maybe I should just, so this is a genus G surface, and we have K alpha and K beta curves, and then W is also a vector. We have K minus G plus 1 coordinates. So we have K minus G plus 1 such W's. Somehow these two numbers determine the third. Okay, so such that each alpha I contains a unique xi, and each beta j contains a unique xj. So what we take one coordinate from every alpha and one coordinate from every beta curve. And we have exactly k, so they must be the intersection points of the alphas and the betas. And one alpha contains a single one, and one beta contains a single one. Okay, so these are the generators. So the set of these points of such k-tuples is, I will denote it with the script S, and so CF hat is just Z2 X, where X runs through this set. Okay, so this is the finite dimensional vector space, and so in order to get the chain complex, we have to define the chain map. So the next thing is to define the boundary map. And as always, if we have a vector space which is given by a basis, then we only have to specify the matrix of this linear transformation on that particular basis. So all I need to specify is this matrix element, which I will denote by nxy. So this is just and then extend linearly. So all I have to tell you what this number is. And this number will be a count of a set. So in order to define that, nxy, let this set be the following. So it's either the empty set, it's the empty if x equals y. So remember these two, so x and y are elements of this generating set. If the two points happen to be equal, so all coordinates are the same, then we just declare this to be empty set. And it's the empty set if there are at least 3 coordinates of x and y which are different. So remember, on every alpha curve there is an
ordered.
No, never. I mean, the alphas are not ordered. I mean, I'm sort of confused. What's the symbol? Probably it's better like this. Yeah, so these are not ordered. And so you have 2 unordered k-tuples, and so some coordinates might coincide and some might not. And if there are at least 3 differing coordinates, then you just declare this set to be empty. Okay? And so now I have to tell you what happens if there are 2 or 1 coordinates which differ. So what happens if there is 1? So here is, say the first coordinate is different and all the remaining coordinates are the same. So there is an alpha 1 and the beta 1 on which we have 2 different points. Well, there are a couple of possibilities. It might happen that these 2 curves sort of prescribe a bigone. They might prescribe 2 bigons, for example, like this. You see, if these are the 2 points, then we actually have 2 bigons. Nevertheless, what we take is the set of those bigons which go from x1 from x to y. So bigons which go from x to y and contain no further coordinates nor points of W. So let me just sort of work on that a little bit. So first of all, if we have these 2 arcs, they might sort of specify a subsurface which has some non-trivial genus, right? Then we don't count that. We just don't take it. If it happens to be a simply connected part of or surface sigma, so a bigone, then it's potential. Then it's a potential element of this set. It has to satisfy these further constraints. What's the meaning of these further constraints? Well, of course, it doesn't have to be an elementary bigone. It might be something like that, say like this. And the first question we ask whether the coordinates on these further curves are inside or bigone or not. If they are inside, so say this is x2, which has to be the same as y2 because this is the only differing coordinate, then this bigone doesn't play. Then we have to examine the domains. It might happen that one of them contains a W, right? Every domain is either a bigon or a rectangle, or it has a base point. If there is a base point inside, then we again drop it away. So we only keep those bigons which happen to go, and I didn't specify what do I mean by going from X to Y. I will do it in a minute, but we just take those simply connected domains which doesn't contain any further points. This is not allowed, for example, something like that. From here to there. It's a bigon between these 2 points and another bigon between these two, but it's not a bigon from here to there. Okay? And so I have to tell you what do I mean by going from one point to the other. So which goes from nor points of W.
Okay, no problem.
So, which ones? Like these guys?
Yes.
Well, if they happen to contain a coordinate from X or Y, then we just forget about our bigon. So we only keep those bigons which are empty, in the sense that they are not allowed to have any W's, and they are not allowed to contain any further coordinates in their interior.
Do these conditions rule out, the heart-shaped bigon?
Yeah.
These conditions rule which is index 2?
No. So yeah, I have to specify some more conditions. So let me just finish. So we also specified what the point measure is. You remember the point measure? Let me just. So every intersection point has a point measure, which is just the average of the multiplicities of the 4 domains. And here we require the 2 points have point measure 1/4. So yeah, I didn't handle Blackboard very nicely. So point measures are 1/4. So this is the rule which sort of gets rid of that kind of a domain, because here the point measure is 3/4 as opposed to what we require. And the final thing is that I have to tell you what do I mean by going from X to Y. So let me just draw again. So the Heegaard surface sigma is oriented, giving an orientation to this domain D, this bigon D, which in turn induces an orientation on its boundary, inducing orientation on the boundary. Well, the boundary has 2 sort of different types of arcs. There is an alpha arc and then there is a beta arc. And we require that we travel from X to Y on the alpha arc. And D goes from X to Y if the induced orientation on alpha goes from x1 to y1. Okay, so we take all these bigons.
So the reason you don't want x's inside the bigon is they'll have the wrong mass left index.
Yeah. So, well, let me just remind you what. So that's the formula for the Maslov index, and so the Euler measure of these domains is always 1/2, because you have one bigon, one elementary bigon, and plenty of rectangles, and then the point measure should be 1/4 in each of the endpoints, so it gives you another 1/2, and if you have a point inside, then it would give you an extra 1. But this is sort of a side remark. We don't have that, right? Or we don't need that here. Okay, and then there is one last case, and I will not give the details of that. It's just the same. So I'm still defining this nxy. So the last case is empty rectangles from x to y. And again, the definition is the same. So in this case, if there are two coordinates in which x and y differ. Right? So there are either 0 coordinates when they are equal. There are at least 3 when we don't take anything. If there is 1 coordinate in which they differ, then we take a bygone if it exists. And if there are 2 coordinates, then we consider empty rectangles. So they look like this. Something like that. So here is an x coordinate. Yeah, okay. This is an x coordinate. This is y, and this is y. And then we are allowed to take this rectangle provided, for example, on this red curve, the x coordinate is outside of that regime, and it's somewhere here. Also, we are not supposed to see any base points in these elementary rectangles. And so the orientation in this case, so say the blackboard is my sigma, is the Heegaard surface, and it's oriented in this way. So we really go from x1 to y2 on the alpha curves, and x2 to y1 on the alpha curves. Okay, so does that make sense? So,
Bygone and rectangle case, these are embedded.
Everything is embedded. So that's why, this is sort of, it's not embedded. There is a twist in it. So we
have immersions that are not many.
Yeah, so we could have, we could have a rectangle like this. Something like that, right? Yeah, but we don't allow that. So in other way, maybe there is a more formal way to do that. So D should be, which is a linear combination of elementary domains, and all the multiplicities are either 0 or 1. Each point measure should be 1/4. Again, we have the same assumption here. Nothing inside, and that's it. Typically, these spaces, these sets are not very big. They are typically empty. And every now and then, they contain 1 or 2 elements. So there is no such case when you have 3. So, for example, it's clear that there are finitely many such domains, because you have finitely many elementary domains, and every such D is a sum of these with multiplicities 0 or 1. So, there is a very easy upper bound of their number. And so this is how we define the boundary map. And now, okay, so the question is...
You didn't describe what this small nxy is. You define this as nxy.
Say it again? Oh, yeah, okay, sorry. So the little nxy is just the cardinality, and we are working over Z2, so we just take it mod 2. Okay, so we have the boundary map, and so the obvious questions are like, first of all, whether we get a chain map, chain complex, and you might ask, what does it have to do with the holomorphic theory? Yes?
So, how do you disallow immersed things?
How do I do what?
How do you get rid of immersed?
Well, so first of all, we define something. How do you get rid of the... I mean,
No, but... Okay, so are there no immersed bygones?
No, we don't allow them. So, D, as every domain, is a linear combination of elementary domains, and these multiplicities we allow to be 0 or 1. So anybody who is outside of the domain should be 0, and who are inside come with multiplicity 1. So I just tried to draw something here, right?
So your Heegaard diagram doesn't have that?
No, we just don't consider it to be, we just don't take these domains into account when we define the boundary map.
So is this the generic situation? I mean,
This is the holomorphic situation.
generically, the projection of holomorphic curve is like this? They are all embedded? Or?
Yeah, I mean in nice diagrams. So in nice diagrams they are always embedded. Well, that's a theorem, right? So
I'm confused because those things could actually exist homomorphically, right? You're just not counting it?
no, they don't. So in a nice domain, in a nice diagram, they don't exist.
Such immersed bigons do not exist in a...
They holomorphically not.
For index 1.
Yeah, index.
Yeah, most of index 1.
I mean, I don't really understand, like, there seems to be no contradiction having such a...
Does that use the fact you don't have a S1 plus S2s or something?
No. I mean, you know, that's okay. So let me just quote this theorem of. I mean, how would you draw like an immersed rectangle, say? So, you know, it would come back at some point, and then what do you do? Okay, and then.
Oh, so that's not a nice...
How you know, you want to go out or you want to close it up? Yeah, that's bad, right? Because then the point measures are bad.
No. Suppose you just close it up.
Where?
The skewed bigon.
Okay. So.
Do the exact same thing and then...
Like this?
Yeah.
Okay, let's do that. So let's see what's the multiplicity of this thing. It's 2, right? It must be a bigon. It must contain a bigon, right? Okay, so let's go to the formula. So the bigon comes with multiplicity 2, and then we still have point measures in the corners. So it will not be a most of index 1 domain.
I don't understand.
Okay, let's start again. So, so you have an immersed bigon, which contains, you know, elementary rectangles and some elementary bigons, right? The only thing which comes with multiplicity must be at least one bigon should come with multiplicity 2.
So I can sort of understand that you'll never get some configuration like this because of the placement of the dot, right? But
No. I don't think you can have such configuration. You just don't count it, neither in the combinatorial theory because I declare what we count, nor in the holomorphic theory because they don't have most of index 1.
I think they do, right?
Okay, let's compute the most of index.
But you don't. Those things don't. The dots inside you don't really count towards your mass of index, right?
These dots?
Yeah. Not those. The ones inside.
These? The dots?
What's there? The intersections.
The intersections I don't count, but the Euler measure I do. Right? So, you know, like this is blue, and then there are these further blue curves, like this. So it takes us a little bit away, right? But so, what I want to say is that there is this bigon. It might not be an elementary bigon, something like this. So there is this very, very inner bigon which comes with multiplicity 2. Do we agree on that? Is that a problem? What do you think?
I don't think that's a problem.
Okay, I think that's a problem. So now at least we pinpointed where. So then let's get to the Maslov index formula. What does the Maslov index formula say? You have to count the Euler measure and the point measure of the domain. Okay? So do we believe in that formula? Cool? Okay. So this little bigon comes with multiplicity 2. Right? And its Euler measure is 1/2. So the Euler measure is 2 times 1/2 plus the Euler measures of all these rectangles, which actually give you 0. So this is my Euler measure. The point measure comes from the...
I think our issue, I think it's the same thing, but I think it's just that the complement, right, has a negative Euler measure in this particular case. So I think it's just really a question about placement of the dot.
Oh, so you want to say this?
Yeah.
Yeah, okay. Whatever. I mean, you know, this will not be empty, right? So you will get you never count these in the holomorphic theory. Okay. So one problem down. Okay. Okay, so we have this chain complex. The first remark is that if we consider the holomorphic theory then we get the same chain complex. So, you know, this statement has to be verified. There is a theorem here. There are actually two theorems, right? The first is that whatever almost complex structure I put on the symmetric power, we'll always get the same chain complex. This is typically what does not happen. You know, if you take a random Heegaard diagram, then the chain complex will depend on the chosen almost complex structure. The homology will be independent, but the chain complex itself might depend. But I gave you a sort of argument last time that for nice diagrams, that never happens. So we know that the chain complex is independent of the almost complex structure, and all is left is to identify with that particular chain complex, which says that, so this is the theorem of Suchurit-Sarkar and Jajun-Wang, saying that in a nice diagram, the boundary map counts only embedded empty rectangles and bigons. Well, strictly speaking, they worked with a one-pointed diagram, but the argument is not difficult if you have a multi-pointed Heegaard diagram.
So this is the case for the natural complex structure on that symmetric product? Or you have to choose a generic?
Well, yeah, you have to, but you know, the answer will be independent of the complex structure. So you choose whichever you like.
So what is the precise statement of this?
For any generic almost complex structure, this holds. Okay. Okay, so now we completely forget about the holomorphic thing and we just stick to our problem, and let's just do one exercise. Well, let me prove a lemma first, or an observation, which sort of makes life very easy. And the observation is that in a nice domain, in a nice Heegaard diagram, sigma of beta w, each alpha and beta curve has a base point on its either side. So, you know, this is sort of the technical way to say it, and in the drawing it just means that you just have your surface, I pick an alpha curve, and I traverse along the alpha curve, and I necessarily have to hit a domain on the right and on the left where there is a base point. Okay? So this holds for every alpha and every beta curve. So somehow base points are close to all the curves. How do we argue? So, you know, we take this classic strategy of arguing by contradiction. So we are in a nice domain, and suppose that there is this curve alpha 1, which doesn't have a base point, say, when we traverse in this direction, it doesn't have a base point to the right. So suppose that alpha has no base point, alpha 1 has no base point on its right side. That would be bad. That would be a counterexample to my observation, right? But what does it have on its right side? So if it doesn't have a base point, it can have only rectangles and bigons. So suppose it has only rectangles. Okay, so there is this first rectangle. This is a sort of an elementary rectangle. Nothing goes inside. Okay, then we move to the right. Again, I have to see a rectangle which has to be sort of the same height because I have to continue this red arc in some way. And then you just keep doing that, and you will never meet a bigon. So what you will see at the end is a parallel circle like this, which means that I found a component of the complement of the alpha curves which doesn't contain a base point, and that's a contradiction. So somehow I want to show you how this assumption, the distribution of base points come into the play. So this is the case when we didn't have any bigon, and then there is this other case where you have a bigon like this, and then you move on, and well, you know, it's either on the other side you have a bigon, which means that you are done, and you again found a whole domain, a whole complement, a whole component without base points, or there might be some rectangles and another bigon, and again you have a component of sigma minus alpha without base points. Too bad, you know. Or we start with a multi-pointed Heegaard diagram, which by definition has a base point in every component. Okay, so this is an observation, and so let's see how can we argue for the fact that we have a chain complex. So lemma CF hat sigma alpha beta w delta hat is a chain complex, i.e. delta square is equal to 0. So this is typically the sort of the turning point of Floer homologies, right, or Floer theory, whether it holds or not. And in case, of course, it's like a baby version of all Floer homologies. It will be sort of a simple argument. So let me just start. Okay, so what do we have to do? The usual story. Take x and z, 2 points, and prove that the coordinate of z in the image of delta square on x is actually 0, or, you know, I mean mod 2. So what do we count here? Well, we have to apply delta hat on delta hat. This is just sum of nxy y for all y's, and then we have to apply it again and take the z coordinate of the image of the result. So let me just write it down very quickly. It's very standard, so we just have to take these sets and take their union for all y's, right? And this statement is just to say that this hat has an even number of elements. So I want to show that this has an even number of elements. Okay, so how can we go from x to z in 2 steps? Well, we can use 2 bigons or 2 rectangles, or we can mix them. So this sort of, let's call it n, and I partition into 3 groups. There are the 2 bigon cases, the 2 rectangle cases, and the mixed guys. So this is a disjoint union of the bigons, the rectangles, and the mixed. And of course, this is a disjoint decomposition of this set, and of course we only have to argue that one of them is even, and then the same strategy will apply to all of them. Okay, so I will just focus on this. I will show that this is even, and then the same argument would apply here and there. And we partition this even more. So this will be the disjoint union of N1 and N2. Because we have two bigons after one another, there are two possibilities. So for the first bigon, there is a coordinate which moves. Say it's x1. For the next bigon, either the same coordinate will move or some other coordinate, right? So is that clear? Okay. The whole thing is very simple. It's just probably I'm not telling it in the right pace or order. But let me just do it. So these are the pairs from this product, the union of products. Two bigons which have the property that disconnects x1 and y1. And this is D1, and D2 connect some other 2 points. So my picture sort of suggests that they are disjoint. They don't have to be disjoint. It might happen that it's like this. So the actual bigons intersect, but the curves which contain the actual moving coordinates, where the x and the y differ, are different. And now I just wrote down the, what we have to do in this case. So this is x1, y1. I'm sorry. So this is x1, x goes to y, and then, of course, this is the same as y, and this should be z, right? So d1 goes from x to y, and d2 goes from y to z, but in that coordinate, x and y are the same because they only differ in the first. And with the same effort, we see that this should be the same as z. Because z differs from y only in one coordinate, so in all the others they should be the same. And now I claim, so this is an element of n x y cross n y z, and all I have to do is to find a friend of this guy. So I am sort of about to define a free z2 action on all these sets, which just means that they have even number of elements. Well, where is the friend? So let's take D2, D1. So the same two rectangles, but now the same two bigons, but now I apply this first. So this will be an element of nx, and now I have to tell you what. So this will be a y2 prime, and this is a y1 prime. And all the further coordinates of x, y, z, y prime are all the same. Then this rectangle, this bigon goes from x to y prime, and this other one goes from y prime to z, right? And it's clear that somehow x, y, z determines y prime as the fourth possibility in this little picture. So every time I have d1, d2, I have a friend, and clearly the friend determines, I don't know whether it's correct, like a husband and wife, or how does that work? These days you have to be careful. Okay, anyhow. So this is the case when we work with this set. We clearly see a free Z2 action. Now we have to worry a little bit about these when we move the same coordinates. So let me just move to the other end of the board. That's a little bit more complicated. It's not that complicated in case of two bigons, but with two rectangles it might take a little more work. So let's see. The idea is the same. I want to find the friend of y. So here is x, there is no real sense of adding indices because there is only one curve which will move. So this is x, and this is y, and this is the alpha curve. And this is the orientation, so we travel from x to y. And now we will travel from y further along these curves, because the two bigons in NB and 1B share the same moving coordinate. Okay, so how can I leave a point y? This is the orientation, so either my domain should be starting somewhere here, because that induces the right orientation on alpha, or I can move in this other direction, because that induces the right orientation of alpha. This is sort of out of the question. These are the quadrants where you come into y, and these are the quadrants where you go out of y. Okay, so of course the two cases are completely symmetric. So suppose that we start in the left side, okay? So we start our domain and then we travel. There is this bigon, and there are two cases to distinguish. So at some point we will reach the z coordinate. We might reach the z coordinate first, or we reach the x first and then the z. Again, the two cases are symmetric, so suppose we reach the z coordinate first, which means that here is my bigon. Oops. So this is the z. Okay? So what did we find? We found a point where we somehow go into our original bigon, but of course this is the same curve, and at some point it should come into x, which has point measure 1/4. So although it came into the bigon, but at some point it has to leave it, right? It can leave it only through the alpha curve, and the alpha curve has sort of two portions. There is one which is inside this D2 bigon, and one which is out. So, it might be crazy and it goes into here, but eventually it should go out. And that will be my y prime. So let's suppose that it doesn't do this little stupid kink. And the more intelligent way of drawing the same picture is something like this. It's sort of more symmetric. You just have to, instead of having such a nice straight alpha, I just bend it a little bit, and this is what you get. So I go from x to y using this bigon, and then from y to z, this bigon. Or I can go from x to y prime using this, and then from y prime to z using that. And again, once you tell me x, y, z, there is a unique way to find the y prime. So they again have friends, and this is all we need for the evenness of that portion. And all you have to do is to repeat the same argument for two rectangles and the mixed guys. And so again, the two rectangles might be disjoint, like this. And again, disjoint doesn't mean that the domains are disjoint. They might intersect each other in such a way. It just means that they move different coordinates, or there is this sort of slightly more complicated case when you have the two rectangles like this. You see one and then the other. So let's shape it like this: one and then the other, or this one first and then this upper one last. Does that make sense? And again, all these proofs need a little planar geometry, and the hardest statement is that when a curve goes into some convex or like a simply connected domain, then it has to come out at some point. And provided you believe that, when I was in school we called it the Posh axiom, that if a line enters a triangle, then it has to come out of it. It's somehow one of the axioms of classical geometry. Okay, so did it convince you that it's a chain complex? Okay, so whenever we see a chain complex, what do we do next? We take its homology. So here is the definition. So hf hat of sigma alpha beta w is just the homology of this chain complex. And as Tom pointed out last time, this is not really the invariant we would like to work with. We have to modify this definition a little bit, and I define HF hat stable of sigma alpha beta W to be the equivalence class of the pair and we just take the number of base points here where a vector space and the number is said to be equivalent to another vector space, to the pair of a vector space and number. So these are vector spaces over Z2, and these are just non-negative integers if provided B1 is bigger than B2, bigger than or equal to B2, we have that, so how is that? V1 is isomorphic to V2 tensor Z2 plus Z2 to the power B1 minus B2. And such a bracket indicates one equivalence class of that equivalence relation. Okay, so unfortunately, this vector space as it is somehow is not an invariant of the three-manifold. It's a well-defined invariant of the Heegaard or the Heegaard diagram, but this is not what we like. We would like to have an invariant of the three-manifold. And somehow we have to incorporate into the definition the number of base points. And this is one way of doing that. We just consider pairs where two pairs are considered to be the same if they satisfy this relation, or we could say like we take the dimension of that vector space and we subtract the number of base points, and that will give us a dimension, and that's the invariant. So is that sort of okay? So then the theorem.
How this tensor product the G2 direction the G2 will be.
So we say that a pair of a vector space and a number and another such pair are equivalent if they satisfy this condition.
That's a tensor power B1 minus.
That's a tensor product and that's a plus.
The power is tensor.
Oh yeah, like this. Yeah. So it's a, you just tensor product it the difference times this two-dimensional space.
And that's because this is really a Heegaard diagram, y connected sum with S1 cross S2.
No. No, the S1 cross S2 comes in at the last moment. This is because when you do a stabilization of this type, then you just...
Connect sum.
No. It's not a connect sum. It's the same. Right? So it's not S1 cross S2. There is, and you put a base point here. Just give me 5 more seconds.
Okay.
Well, 5 minutes. First of all, let me just erase this thing. And so here is the theorem. So, theorem. So suppose that D1, D2 are two convenient Heegaard diagrams of Y, three-manifold containing no S1 cross S2 summoned. Then HF hat stable of D1 is the same as HF hat stable of D2. So remember what a convenient diagram means. So D1 is defined by taking a pair of pens Heegaard diagram for Y. So this just means that we take a Heegaard decomposition, and each handle body is captured by a pair of pens diagram, alpha and beta, and then we just did this refinement. You remember, if we had a component like this, a pair of pens component, an alpha pair of pens where the betas intersected like that, then I just added one more curve and put a base point here and there. You remember that? So when the convenient diagram means that we start with a pair of pens Heegaard diagram, we do this refinement, and whatever we get, we call it a convenient Heegaard diagram. And the statement is that if we have two convenient ones, then this stable Heegaard-Floer homology is the same. And of course, every three-manifold has convenient. Every three-manifold with no S1 cross S2 summand has convenient Heegaard diagrams. So this is really a diffeomorphism invariant of the three-manifold. So how do we prove such a statement? So the idea, last time I claimed a theorem. So last time we had this theorem that D1, D2 convenient diagrams are nicely connected, i.e. there is a sequence of nice diagrams such that the first is my starting D1, the last is my ending D2, and these are all nice. And di and di plus 1 differs in a nice move. And there are four types of nice moves. There is handle slide, isotopy, and two types of stabilizations. And so in order to verify this theorem, we only have to show that whenever we go from D1 to D2 in this nice sequence, then at every step we don't change the stable Floer homology. We will change the chain complex, but not the Floer homology. Well, I will show you what to do with the stabilization, because that's very simple, and then maybe we will spend some time on the isotopy. Okay, so this statement, okay, so let me just write it down probably. So proposition: if D1, D2 are two nice Heegaard diagrams, differing in a nice move, then HF hat stable of D1 is the same as HF hat stable of D2. So two nice diagrams, which I get D2 from D1 by applying a nice isotopy or a nice handle slide or a nice stabilization, does not change this stable Floer homology. And clearly, based on this argument, based on this result, the theorem follows from this proposition, right? So we only have to check it for the four moves. And let me just remind you what the four moves are. So let me start with the type G stabilization. This was when we had a domain with a point. And we just added a genus. plus these two curves. Right? So I turned, is that clear? Okay, so I claim that in this case somehow the chain complex doesn't change. So this move keeps the chain complex unchanged. Indeed, if you have an intersection point in the original diagram, there is only one way you can pick your coordinate on the new curves, because they don't intersect anyone else, they intersect each other in a single point. So if you have diagram D1 and diagram D2, each comes with this set of generators, S1 and S2, then a bijection can be set up by sending x1 up to xk to x1, xk, and let's call this intersection point x nu. And this is a bijection, and it happens to be a chain map because, somehow there is no empty bigon or rectangle can start from that point, because in every quadrant near to that point there is a base point. In fact, the same base point can be sort of moved to each side. So that's the easiest. You don't have to do anything. Right? Okay, let's do the other stabilization. So this was the stabilization which increased the genus but kept the number of base points fixed, right? We didn't add new base points. The type B is standing for base point stabilization, where we keep the genus fixed but we increase the number of base points. So here is this domain D with the base point. And now I add two curves, an alpha and a beta, like this. And the base point, right? So what happened in D1 and D2, so W1 became W2, which is W1 union, let's call it W nu. So we just added one more point. And what happened with the chain complex? Well, every intersection point, old intersection point, has to be promoted to be a new intersection point. We have to pick a coordinate in these new curves. There are two choices for that. There is this upper guy and the lower guy. Right? So we sort of doubled the size of the intersection points. Well, doubled in the sense that every x now refers to x up or x L, right? And how do the boundary maps go? Well, there are the old boundary maps among the old points, and here between the new ones, nothing can go out in this direction because there is a base point. Similarly, nothing goes out in that direction, and then nothing can go out in this direction either because there is a base point here. So the only thing we can have is like these two rectangles. So the moduli space between XU and XL contains two elements, which means that the boundary map of this subcomplex is just 0, right? Because we work mod 2. So at the end of the day, we get that CF had D1. So that was the old complex. That the new D2 is the same as CF hat D1 tensor. These are two generators, Z plus Z, Z2 plus Z2, and the boundary map is 0. Right? So this is exactly this is the answer for your question. This is where these Z2 plus Z2s come in. Okay, so you have to do it a couple of times. Well, for one type B stabilization only once. But we also increased the number of base points, so the stable Floer homology didn't change. Okay, and finally there is a nice handle slide and nice isotopy. And so I will just sort of show you the idea of how to deal with nice isotopy. Cool?
You can just attach a handle.
Of S3, you know, it's a spherical Heegaard diagram which involves two curves. Morally, for S3, you have the spherical Heegaard diagram which doesn't have any intersection points, right? It doesn't have alpha curves either. It's a genus 0 Heegaard decomposition. But now we take morally this Heegaard diagram for S3, and this is what we connect some with.
Well, no, but you can imagine there's a handle from that point to the other base point, right? One of the other base points, and then it actually would be exactly the same as next.
You can do that, and then you only need one base point, but you still pick up this, but somehow technically the whole approach would collapse, right? Okay. Yeah, you know. Okay.
Can I ask you one?
Yes.
So here somehow this Floer homology is the equivalence class, right? So instead of taking that equivalence class, why don't you take the stable Floer homology as the V1 tensor with G2 plus G2 tensor product of the B1, the number of base points? That seems to be all that.
No. So let me just... Okay, let's talk a little bit about that. So of course it would be more elegant. So the invariant is really this. So HF hat of the 3 manifold is just HF hat of the diagram tensor Z2 plus Z2 on the power, the number of base points minus. So somehow you should be able to show that this vector space is divisible by that. So it has a dimension d, and the d is sort of divisible by the dimension of that.
Put it on the other side.
Yeah, so you know, it's just the sad fact is that we couldn't. You know that it's true. These are the most annoying statements. You know that it's true. You know how to prove it using the holomorphic theory. I just don't know how to prove it. This combinatorial theory so that this vector space decomposes as a tensor product of something and this one. In other words, its dimension is divisible by the dimension of this thing. We know it's true, but we don't know how to show it. Well, we know one way to show it, but we don't want to use that. It's like having a midterm and you tell to the students that they are not allowed to use cosine and sine, you know. Then of course they do, and then you are in trouble. So does that answer your? So you want to put a plus here, but that's wrong. That won't be an invariant. You should put a minus here, which doesn't really have a meaning, but it just means that it assumes a divisibility for the dimension, and I don't know how to prove that. I was cheating a little bit, actually.
This equivalence relation can be written in that way, right? Instead of putting every this tensor vector on the right hand side, you can put half of them on the left hand side.
Yeah, the equivalence relation.
Yeah.
Yeah, but that wouldn't change anything. I mean, what's the point is that you still the result is the invariance of the equivalence class, and we can't go. You know, it would be nice to represent every equivalence class by V1, right? But we don't know how to do that with chain complexes.
Still, we can find the equivalence relation on the chain level, not only on homology level. So I
Okay.
hope to chain homotopy and that new equivalence relation on the chain complex, you may choose the invariance theorem on chain level so that we can extract something further than homology.
Yeah, so I mean, you know, then you have to go into how you prove the invariance, right? And yeah, I mean, at one day I'm hoping to get rid of this thing, and then it's just I don't know at the moment how. And of course, you want to extract more things. You want to have the spin C grading, the Maslov grading, all these additional tools, and we practically know how to do that, but it's just, you know, it's not that entertaining.
At this moment, the equivalence relation just forget these grading things and just
Yeah, at the moment, at the moment,
the dimension only. Right?
yeah, at the moment we just the invariant is the dimension of the vector space, and you can refine that.
Maybe this is not so relevant, but if you
That's okay.
coefficients, then that right-hand side really disappears. Like
You do what?
twisted coefficients.
Twisted coefficients.
You don't have the stabilization issue.
That's true. Yeah. Why don't you do that? I don't know. I mean, this is sort of the simplest version, and it's like, like a backbone, and then you can put all these extra decorations. And let me just give you, I don't know how much time do we have, like 10 minutes or so.
Yeah, you started a little late.
Well, let me just 5 minutes. Okay, so stabilization. No, isotopy. Okay, so how does an isotopy look like? So you have your Heegaard diagram like this, and then you have this nice curve which starts at some alpha curve, and then it passes through some betas, and then it stops. And this means that you have to do this isotopy like this, right? So that's a nice isotopy. Of course, there are some requirements that in the back it should be a bigon, and this either a bigon or it has to contain a point, and so on. But now we are sort of very on the chain level. So what happens? You all have in the new diagram, you all have your old intersection points. So if this is the corresponding set of intersection points is S1, then here in S2 you have all the S1s, plus you have new intersection points, namely the ones you develop when you do this finger move. Well, there are sort of two types, because there are the ones which sort of fell to the left of this gamma and to the right. So I call them F1, Fn, and these are their brothers E1, En. And the rule is that having the orientation on the surface, you always go from F to E by passing through this bigon. Okay, so let's call the collection of Fi axes, and then there are the Ej axes, right? And so from now on, it's sort of linear algebra to prove, there is a little diagram chasing and linear algebra. And the idea is the following. So let's take K to be the vector space spanned by these Fi axes together with their D images. Okay, so it's like a subvector space. Oh, obviously it's a subcomplex because D square is 0 and the D's of these guys are in this subvector space. So here are two claims, and I will sort of indicate the first and leave out the second. So the first claim is that H star of K delta hat restricted to K is 0. That will be easy. This is what I will indicate. Then once you have a subcomplex, then we can take the quotient complex, right? So this is a subcomplex of S2 giving the Heegaard Floer homology of D2, and it gives a quotient complex, and there is an induced boundary map which I will denote by delta Q. And so the next claim is that Hf hat of D1 is actually the same as Hf hat of this quotient complex. This is not so hard to see. I mean, first of all, the dimension of S1 is the so S1 appears here, and what we do, we just take this K, which is of the dimension given by these elements. So at least as vector spaces, the chain complexes CF hat of D1 and Q are equal dimensional vector spaces, and all we have to find is a map between these two isomorphic vector spaces, which is actually a chain map. So that's sort of a little pain. Let me just argue for this. So in order to show that this boundary, that the homology is 0, well, clearly all we have to do is that, so these elements are all images, right? So they don't play in they are killed by these Fi axes. All we have to convince ourselves about is that none of the Fi axes have 0 boundary, right? And so here is the claim. That the boundary of such an element starts with its friend, plus there are some extra elements, and these have coordinates of the type from S1, so from elements which doesn't have any F coordinates, or E and F coordinates, or of Fj y's. So somehow from the rest, nobody can actually kill this guy, so this will always survive, and so the map is non-zero. So let me show you this last statement, and I think that will be a good place to stop. So here is F. Let's take this Fi. So what does it mean to take the boundary of that map, of that point? You know, all the coordinates are sort of far away. All we have to examine is which are the points we can reach from this by empty rectangles and empty bigons. And we take this orientation convention that this should start either in this direction or in that direction. And all I want to show is that if I go from Fi to some Ej, then it should be Ei. So how can I go from Fi to the Ej's? Well, there are two ways to do that. Either I start in this direction, which means that I have to go all the way around this curve. Right? I have to pass through like this, and then back here, and then stop at some Ej. I claim that it is impossible, and this is because, remember, in both sides of any curve there is a base point. So in this travel we must have hit a base point, which is too bad because we are looking for empty domains. So I cannot start in this direction. So the best I can do is to start in this direction. I go, I pass all the F's, and then I turn, and then I start to pick up the E's, and I stop at certain E, right? So what did I pass? I definitely passed the bigone. So although I have to count either empty bigons or empty rectangles, we are forced to count empty bigons because there is an elementary bigone here, which means that the image is some Ej times the rest of the coordinates should be the same because they can only differ in one coordinate. And now a little computation shows that it should be the same level, otherwise you cannot get back. So, you know, it's far from being the complete argument, but I hope I gave you some taste of, like, you know, working a little planar geometry plus suffering through these combinatories gives you like this simplest version of Heegaard Floer homology. And again, if you spend a little more time with it, then we can recover the spin C structures, the grading, orientation, so it can be defined over Z. You can get not Floer homologies, link Floer homologies in the same way. But I think we'll stop here. Thank you.